So now we are testing the second specimen, which is,
Aluminium.
and we're on the same screen after testing the steel setup. So now he needs to change the method. So he's going to method, open method, and earlier we went to SMT lab, UW Medicine, and chose 307 tension test rounds with extensometer. Even though we did not use the extensometer, now we will use only tensile test with rounds. So yes, he chose the correct method. And he clicked on OK.
What he's going to do now?
Now he needs to click on the test tab so that he can look at the output channels, which are the crosshead displacement on the left, and the right one is the load cell in pounds again.
That's correct. Needs to make the first adjustments like we did for the steel specimen. And after we have set everything, here you go, with the other view has come up.
Oh, you can see me. That's
Pretty awesome recording,
Yes.
I must say.
yes, I'm famous, huh? And notice that we cannot see the extensometer channel here because it is not connected, and it's because of the method.
So we're loading the sample as we would loading a steel one, but this time it's just aluminum.
And again, we need to insert the specimen first in the top jaw so that we can nullify the weight of the specimen.
And leave some gap from the top head of the jaw and the specimen head.
And notice he forgot to zero the value of the load. We should zero the value of the load after inserting the specimen in the top jaw. But maybe he will do that before tightening the lower jaw. Let's see. I bet he will forget. But let's see. So now he's
Manually.
bringing down the specimen down manually. Oh, he remembered to zero the load. No, right?
Yeah, that's always a problem when you are doing such experiments. But let's see what.
Do you think he's nervous while performing the experiment?
But he doesn't look like.
Yes, sometimes I am. So you break materials, you know.
You do need some confidence.
Oh, so he remembered to zero the load.
So yep. So here he zeroes the load, and now he is tightening the jaws.
And after tightening the bottom jaw, there is some non-zero value of load. The value of load increased, and this is the actual load because of the gripping action of the jaws. So we should not zero this, right?
No, we should adjust the position of the jaw so that the load says zero and not zero it.
So he used the vernier scale on the handset to do that. So how many speed control modes are there?
Well, there are 2 on the machine and the computer interface, and 1 for fine adjustment. Am I correct?
Yes, wow. Yes, this is the fine adjustment using the vernier scale. And notice how small is the movement of the crosshead in the channel of the crosshead displacement. It was 1/100th of an inch.
Well, that's a lot.
That's accurate, wow.
Yeah.
So now he clicked on start the test.
And you see there's an error on the screen. That's because you forgot to turn the manual mode on the handset off. So here he turns it on or turns it off here.
We're
Yes.
good to go.
Yes, so that the control of the crosshead is with the software and not with the handset. And now he's entering the sample ID, which is tension test 307 aluminum.
But once this is done, and then you need to measure and mention the diameter of the specimen so that you get all the information that you need once the test is over.
So here he measures the sample with calipers.
And the ASTM standard is 0.35 inches for the diameter. Let's see if this is accurate. Oh yeah, so this is around 0.352, so very close to the ASTM standard.
So now we'll enter the gauge length, which is the distance between the 2 dog bone ends, and that will measure the specimen length. Once this is done, he's using another specimen to test it because apparently both of them have the same length. So he's measuring the gauge length, and then the values will be entered into the computer interface, after which the test shall begin. So the values are being entered into the computer interface.
Oh wow, you can see me with the mask, huh?
Yeah, and the test is about to begin.
Oh, wow.
So, as you can see from the two displays, and we try to make it as clear as possible. The test has started, and the crosshead is slowly moving upwards. You can see on the computer panel that the crosshead is increasing, and
2,000 pounds for a displacement of 0.08.
that's a lot.
Yes,
That's
but this
pretty
is not as stiff as the steel specimen, huh?
Yeah, that is not as stiff.
So
But-
Ed, the steel specimen failed. Do you think this will fail?
No.
Yes, I know you're kidding.
I stayed aware of this, but I think it will. But probably not as much as that of steel. What do you think?
Oh yes,
Yeah.
this is less stiffer.
Yes. So we can see the curve going up, as you can see on the computer panel, though it's very faint, but it gives you an idea.
So the value is 4,100 pounds,
With across the displacement of 0.21.
and we're in the linear region, right?
Oh, I think we're,
Almost crossed the linear region, huh?
yeah, it just crossed the linear region.
Mhm.
So now the deformation is much greater for the amount of increase in force or the load.
Wow.
You can see the detour from the linear regime. We are entering into a non-linear region right now, and the corresponding values as you see on the test screen.
Mhm. And also there's uniform deformation on the specimen till now. There's no signs of necking as of now.
The cross section is fairly constant, and the values are quite different from what you might observe on a perfectly elastic material. So you can see over here that we have almost deviated a lot from where we started from, and
From the elastic limit too.
yes, and you can see the corresponding load.
So we just reached the ultimate tensile strength. Now the load is decreasing. So necking should appear very soon, if not already.
Yes, there is necking, although we cannot clearly see that in the video.
It might become prominent in a
Yes.
while.
Oh, I think we can see it now.
Yes. It's becoming more prominent, clear, the cross section.
Wow, this was loud. And the failure mode is a ductile failure. The failure plane is at 45 degrees. That's interesting.
That's pretty interesting.
Mhm.
And as always, you first need to
Remove
tight-
the specimen
Yes.
and then click on the message on the screen. Otherwise, the crosshead will move and your specimen will jam.
And that might destroy the grips, as we said already.
Oh yes.
So now that we have it, we're comparing two specimens, one broken and one, the original one. But as you can see over here, there is not much difference from the one that we saw for the steel specimen.
Mm-hmm. Yes. So he's showing the failure plane, huh? It's at 45 degrees. Ductile failure.
That's pretty interesting. And we can see two different materials that we just saw. One has a cup and cone failure, and the other has a 45-degree angle cut.
Mm-hmm. Now, so that is the end. But did they forget to save the data? Oh no. So now you can see the stress and strain curve. It looks different from the steel in the sense that, or this is ductile too.